So today we are going to cover, we've done all the basic derivatives. We have one last derivative rule, and we're going to try and spend a good time on it, because once we get this one in hand, the next 2 days will go well. So today is kind of a linchpin day for the next couple of days. So today we're doing chain rule. Next week we'll do implicit differentiation, related rates, and then that wraps all the new material for the next test. Okay, so David, I think I may have computed wrong. And then we review on Monday and then have the test.
Well, that sounds about right.
That sounds about right, on the 9th, I think. Okay. Wednesday, not next Wednesday, but the Wednesday after that. Okay, so let's look at the chain rule. That's what we're doing today. Before we talk about the chain rule, we need to back up. We need to back up and talk about algebra of function, and particularly composition of functions. You guys remember composite functions? F of g of x. We've actually been using it this semester. Every time we write this, f of x plus h, what are we doing? We're taking this whole new function and sticking it in everywhere we used to have an x. Some people like to think of it in terms of boxes. You put an x into the first one, g of x, and then whatever comes out goes inside the next one. Some people like to think of it that way. That's fine too. This is a good way to think about it when you're thinking about domains, actually, because if it can't go in here, it can't get through it. If it can't go in here, it can't get through it. So it's a good way to kind of get your domain for the entire composite function. So, so let's do a couple. So if you have, so here's an example. So if you have f of x equals x plus 2, and g of x equals the square root of x. Okay, we're going to find two things. We're going to find f of g and g of f. The order matters. Okay, so I should have written it over there. All right, so let's look at f of g of x. What does this mean? This means, remember, whatever is in here goes in everywhere I used to have an x in the original function. So what was my original function? It was x, which is now square root of x, plus 2. So this g of x, this right here, went in everywhere I used to have an x. All right, so let's back up. Tell me the domain of the first one. What is the domain? What kind of a shape is it, and what is the domain? It's a line, so we know the domain is all reals. Is there anything you can't put in a line? It goes the whole distance. So here we know the domain is all reals. What about this one? What kind of a shape is that? Let's make the shape. Everybody make the shape. Yep, yeah. Really, everybody. It's a win, okay. I may have you do all the shapes by the end of it, just for fun. Okay, so what is the domain of this?
0 to infinity.
Yeah, you can only take the square root of a non-negative number. So 0 is okay, and positive. So here we know that the domain is x greater than or equal to 0. Okay, so what is the domain then of this one? And this is where this sense of kind of going through different stages is helpful.
It's the same.
Well, in this case it will be. The first one I have to get through is here. So going through here, what limitation do I pick up when I go through g of x first? I pick up this domain limitation. I know that x now can't be greater than or equal to 0, or I can't even get through this first stage. Once I'm through that first stage, are there any more limitations? No. So that means that my domain here is whatever the smallest bit is. So I just have to be greater than or equal to 0 to get through the first stage, the square root stage, and then I don't pick up any more limitations after that. Okay, cool. All right, so now let's look at the other way. Let's look at g of f of x. So again, that says f of x is now going in everywhere I used to have an x. So what was my original function? G of x was square root of x. So that means that this whole thing goes in there. So f of x is x plus 2, so it's going to go under the square root. So now we need to think a little more carefully about the domain. So let's again draw that picture. We're going to go through f first. Do we pick up any limitations coming through f? No, it's all reals, it's just a line, so no problem here, everything goes through. Now when I come through here, but I have to be a little bit careful because what comes out? What comes out is x plus 2. No limitations, but now I'm going through g. What do I pick up here?
X
I
has
know,
to be greater than -2.
right, I know the inside is greater than or equal to 0. The inside of the square root, the input to the square root, that's another way to think about it. The input to the square root has to be greater than or equal to 0. What is the input? X plus 2, so go ahead and write it down. X plus 2 greater than or equal to 0. Now I know what my domain is. You're right. X greater than or equal to -2, or in interval notation, that. So does that sound vaguely familiar from pre-calc? It's not something we spent a lot of time on pre-calc, but this is why you did, because we're using this idea today. Not so much the domains, I just bring that up just to kind of refresh your memory about the whole composite thing. But the important part is going to be sort of identifying the stages or the inside and the outside function. Sometimes people talk about it that way. If you look at this is the inside function. It's the thing you have to go through first. The square root then becomes the outside function. That's the last stage. So if you can identify the stages, inside and then outside, or if you can look at it inside and outside is the last thing you would do, kind of on the outside. Okay, so let's find, let's just do some more examples of that, kind of identifying inside and outside functions, because that's going to be important for what we do today. All right, so here are two functions. So identify for me the inside and the outside function. Bearing in mind there may be more than one right answer. There is more than one right answer. So take a minute and think what you think the inside function and what the outside function.
We haven't written.
Written what?
If you write f of g of x.
Oh, no. These are separate examples. So here's example 1 and here's example 2. So look at g of x and think of how you, if you were going to write this, yeah, as like h of, I'm running out of letters, h of q of x, I don't know. I'm running out of letters. So if you were going to write it as a composite function, what would be the inside function and what would be the outside function?
Right.
That's all. And then same thing down here. Yeah, so two separate ones. Yes?
Is this the x squared or x cubed?
Yeah, I wrote in the notes x cubed. Do you want me to change it back? It doesn't matter so much. Okay. X cubed. No, from my notes I wrote x cubed. I usually when I pick examples, I try to pick examples where I don't use the same numbers anywhere, because that way it makes it really obvious in your notes. If they're both 3s and then a 3 ends up in the answer, which 3 did it come from, it's not always clear. So I usually try to pick different numbers. So, but that's what's on the notes online. So. All right, so do you guys have some ideas?
I mean, an idea, you can never really know, could you?
Sure. And, well, because there are multiple right answers. So give me your answer. What do you think?
I guess h of x would be cube root of x.
That's the outside
And
function.
Q of x would be 1 plus x to the third.
Yeah. Yeah. Or let's write this a different way. Let's use some better letters. The better letters we want to use, let's use E for like exterior. And I know, I don't want to use O for outside. This is what they use in the book. So E for exterior, I for inside. Does that make sense? So I'm taking this whole thing and sticking it inside a cube root. Is there another way to do this one? Anybody see another one? What about this one?
Right.
Would that one work?
Yeah.
Now I'm going to take an x squared and put it in everywhere I had an x. Yeah, I could back to, or x cubed, sorry, x cubed. Yeah, that would work. This, for our purposes, is the better one. You want an outside function that's pretty complete and an inside function, you know, a polynomial inside function, totally fine. So of these two, this is the preferred one. And that's the one that seems more obvious, I think, anyway. What about this one? What is the inside of an exponential? Where's always the inside? The exponent. right? That's the thing, you're gonna take whatever x is, multiply by -2 first, and then you're gonna exponentiate it. So when you're looking at an exponential function, the way I would probably write this is the inside function is just the exponent. And the outside function is pretty much everything else. 50 e to the x. So for exponentials, the inside is always the exponent. That's the easiest thing. Because this is an easy derivative, and this is an easy derivative. I mean, that's where we're going to go with this. Note that how I've written these, though. I can take the derivative of this, and I can take the derivative of this. And so when we concentrate on the outside function, we're concentrating on the structure of it. Okay? Do we want to do another one, or is this okay?
Yeah, let's do another
One more, okay? All right, so let's do this one. So this is not the note, so going rogue again. I know, it's really dangerous. All right, let's do. Aha. That's too easy. That's better. Because the first one isn't even an inside-out, it's just 3 times plus 1. Multiplied by a constant, add a number, that's not interesting, that's boring, that's an easy derivative, that's not complicated, so I don't need that. All right, so now again, we're looking for an inside and an outside function. And so what you're looking for when you're looking for the inside-outside pattern is you're looking, when I'm reading across, I'm saying 3 times something squared plus 1.
Oh, okay.
The something then becomes the x of your outside function. So 3 times something squared plus 1, 3 times something squared plus 1. What was the something? Okay, so 50 times e to the something. What's the something? Right there. Cube root of something. Cube root, there's the something. So I'm going to use something a lot, actually. I know it's not very mathy, but that's okay. All right, so the idea between inside-outside functions is actually you can talk your way through it, and everywhere you put in a something because it's too complicated to say, that something now becomes your inside function. Can you have like 3 layers? Absolutely. You can just layer, going further and further in. We're not going to do that just yet. Okay, so that's sort of inside-outside functions. So let me define the chain rule. And the reason we need the chain rule, let me give you an example of a problem we don't know how to do yet. All right, so if I had this one, I'll just start with these two. So if I have this, can I find that derivative? What do I need to do? I can, and you can too. In fact, you did it on test number 1. At least you were asked to do it on test number 1. How would I handle this? I can't handle it as is. What do I have to do? Distribute, multiply out. So I could take this one and multiply out. Right. And when I multiply out, I'm just going to get 25x squared plus 20x plus 4, I think. And that's an easy derivative. I can do that one.
Right.
What about this one? Yes.
So, I mean, clearly you're showing us like the chain rule and stuff.
Oh, I haven't gotten there yet.
If you separated them into 2 easier functions, did the derivatives and then put them back together, would it do the same thing?
Yes, and you could do that with this one. You could, no, we don't even know how to do that yet. Because if I separated this into this one, x to the 4th minus 5 squared times the square root of x to the 4th minus 5, I could do that.
Right.
But do I know the derivative of square root of something? No, I only know the derivative of square root of x. That's not an x, that's a something. So as soon as you find yourself with a something on the inside, you don't know how to do it. In this case, something squared, well, easy, multiply it out, no problem. In this case, there's nothing I can do to simplify this, to get down to just x's, which is all we know how to do so far. So here's the chain rule. I'm going to come back to this. So here's the chain rule. Chain rule says, if you have a function that is a composite function. Okay? It is a composite function. In fact, you could write it this way. This is, an outside function, an inside function. I could write it this way, where u is my something. Okay, so I'm saying y equals square root of something, square of something, ln of something, e to the something. Okay? So I know the derivative. So let me give you, it's much easier to do with an example. So I'm going to do it with an example. So we don't know how to do this one yet, because it's not e to the x, it's e to the something. So it is not a basic. I could write this as e to the u. It's called a u substitution. You may have seen that before, actually. If I call it e to the u, well, now do I know how to do this one? That looks pretty. I know e to the u, so I can find this dy du equals e to the u, no problem. Because that's just an e to the u. Derivative of e to the u is e to the u with respect to u. What am I looking for? I'm actually looking for dy dx. Did I do that? No. I only did the derivative, sort of the outside piece. And this is not actually how this works, but it's a good way to remember it. What are you left with? dy dx. So this is telling you what you need to do. We're not going to actually, I'm going to take that off. That's just a way to remember it. We're going to take the derivative of the outside function, and then I'm going to multiply by the derivative of the inside function. So that's a lot of times how people will say the chain rule. They'll say the chain rule is the derivative of the outside function times the derivative of the inside function. Because when I take the derivative of the outside function, simplifying it, it's with regard to the wrong variable. I'm not there yet. So I need to convert to the next variable. And so I do that by just taking the derivative of the inside function. So altogether, my dy dx, for this example, would be the derivative of the outside. Leave the inside alone. You haven't dealt with that yet. You're only taking the derivative of the outside. Times, what's the derivative of the inside? 2. It's really that easy, right? So this one would just be 2e to the 2x. So chain rule is this, the derivative. The first question you ask yourself is it a basic function? As soon as you use the word something in it, it's not basic. So this is e to the something. That's not e to the x. If you can't say e to the x, ln x, x squared, square root x, if you can't just say the x, if you have to say something, then it's not basic anymore.
Wouldn't it be EU times?
But what is u?
I thought EU was just E.
Where did I get u from? That was a simple replacement I made. I said, well, let's just say that, let's just call 2x equal to u. Let's just call it that. So if I call it that, then this e to the u is really e to the 2x. So when I'm doing a chain rule, I don't use u's. Some people do, I don't. When I'm using chain rule, what I'm thinking is derivative of the outside times derivative of the inside. Derivative of the outside times derivative of the inside. The important thing is when you do the derivative of the outside, you don't mess with the inside. The inside, it's like you're doing two separate pieces. You can't handle them at the same time. So let's do some examples. I think it'll be better. So,
Should we write that
yes,
out in formula?
Yep, I'm getting ready to. Yep.
Like you kind of just were like, yeah, derivative, and you just like wrote a number.
All right,
and
so-
then it's
so-
like, oh,
Derivative is the derivative of the outside, leave the inside alone, times the derivative of the inside. Or derivative of the outside times derivative of the inside, which is really how I remember it. I do not remember this in formulas. Same thing when I'm doing product rule or quotient rule. I have a running English word sentence phrase in my head. So same thing here. I don't think this. I actually say this in my head. So let's go back and do several examples. So the first one we had was this. What is it? Squared? Squared. Okay, so we already said there's one way to do that, which is to multiply it out, and then I have a basic polynomial. We've done that way already. The other way is to recognize this as a chain rule. Is this x squared? No, it's something squared. So that means the something, 5x plus 2, is equal to the inside. So I've got something squared. Okay, so if I go to do the derivative then, first, so a lot of times what I like to do is, if I can, circle the outside function and underline the inside function. So here's my inside function, there's my outside function. So it tells me which one to do and how to handle it. So what's the derivative of a something squared? X squared would be 2x. So something squared would be 2 somethings. Remember, you leave the inside alone. So this is coming from the derivative of x squared goes to 2x. So that's where this 2 times this. Am I done yet? No, because I've only handled the outside function. Now what's the derivative of the inside function? Just times 5. And so altogether, 10 times 5x plus 2. You can multiply it out if you want to, but a lot of times we don't, because a lot of times we want to know where's the tangent line horizontal. I'm going to set it equal to 0, so no reason to multiply it out unless you need to. Clean up the, combine the numbers. But so is that easier than foiling it out? I actually think yes. So identify the inside function and the outside function. Take the derivative of the outside function times the derivative of the inside function. All right, let's do a more complicated one, and that will actually make it easier. Yes?
So, if you're looking at, let's say, please don't do this to me, but
I will.
if you're looking at, like, let's say, you see one function and it clearly is an exterior, interior function multiplied by another function that is just a regular function, you would then use the chain rule to get the part of
The product rule.
the first one, and then use the product rule.
Combine rules. Oh yes, we're going there. See, it's not his fault. It's already in my notes. He didn't ask for it, and I did it for him. It's
Probably like
already
I'm
in-
gonna
But
get
it
it
is.
wrong on the test.
No, you're
just
not.
because
No,
I'm
no, no,
that
no,
bad.
no, no. So let's keep going, because yes, we are going to combine rules. So let's look at this one. You have this one. Y equals x to the 4th minus 5. Again, I was trying to use different numbers, and I didn't. Can I really change this to a 7? I want to change this number to a 7 because it kind of disappears. It's not something we really have to deal with much, and that will just make it clear where all the numbers come from. So I'm looking at this. If I had this, do I know the derivative of x to the 5 halves? Yeah, that's a plain old power rule, very easy. Do I have x to the 5 halves? No, I have something to the 5 halves. So something is my inside, to the 5 halves is my outside. Okay, so when we go to do the derivative, handle the outside first. So what is the derivative of x to the 5 halves? 5 halves comes down in front, and the exponent becomes 3 halves, right. So 5 halves. And if you need to, write it that way, and then stick the inside in. You haven't dealt with the inside. You don't get to do it in one step. Just like the product rule has 2 terms, and the quotient rule has 2 terms in the numerator, the chain rule has 2 pieces. You cannot do them in one, just like you can't do the product rule in one. So this is the first piece. I have only dealt with the outside. Now I need to go deal with the inside. So now what is the derivative of the inside?
4x cubed.
Anybody else get that? 4x cubed? Because it's just the derivative of that. So that's why I like to underline and circle, because when I underline the inside and then I go to do the derivative of the inside, it kind of helps separate them out for me. And then again, you just combine them. So 4 times 5 halves, 4 cancels to 2, 10, so 10 x cubed, x to the 4th minus 7 to the 3 halves. Oh, this is a good one. All right, let's try another one. You guys try this one. Y equals, I'm skipping one. Actually, then we're coming back. Try to write this down. I know you don't like the W, that's why I threw it in there. Got to get used to different variables. Okay, so I'm trying to find G prime of W, so you guys give this one a go. What's the first thing you have to do, actually? Could I even do it the way it's written?
I mean, you're separated.
Well, yes, but importantly, I would rewrite this first. Square root becomes what? You need to write it as a power. We don't know how to do square roots, we do know how to do power. So anytime you see any kind of root, you always have to rewrite. Now we're ready to do chain rule. So take a look, circle the outside, underline the inside, derivative of outside times derivative of inside. And if you have to come over here and write next to the 1/2, that's the outside function you're dealing with, just if it helps you to write that off to the side, just to kind of, take the inside out of your brain while you're doing the outside function, that's fine. If you have an answer and it looks like your seatmate needs a little help, feel free to look over and see if you can help them out. All right, so what's the outside function?
Exterior?
Yeah, the exterior function.
You were already next to it.
Yeah, well, I did, didn't I? All right, and so what's the inside function? Is that? So I see that 1/2, but it's not, so your first question always when you're taking the derivative is it a basic? If I can't say W to the 1/2, X to the 1/2, T to the 1/2, single variable to the 1/2, it's not basic. It's something to the 1/2. So to the 1/2, that's my outside function, the something is on the inside. So the first thing I'm going to deal with is the outside function. The derivative of X to the 1/2 is 1/2 to the negative 1/2. That should be old hat by now. If it's not, you need to do a lot of practice because this part, no, really, this part should, we've been doing that for a few weeks now, a couple weeks, so that should be old hat. What goes in here? I haven't dealt with the inside yet. You can't deal with the inside until you get past the outside. Now, what's the derivative of the outside? I mean the inside? -1. Combine it all, -1/2, 4 minus W to the -1/2. Yes?
You're about to.
Oh, thank you. Except I started it late, so somebody let me know when it blacks, and then I'll, but thank you for the heads up. Okay, so let's just do a few more. So here's one that actually has a couple of different ways to do it. All right, so I would like for you to find this. d dt of 1/t²+4, did it again, squared. Didn't use different numbers. Yes?
So for the final answer, could you leave that -1/2 up there? Or
Yes, you could leave it this way, or you could write it you could write it this way in the denominator. Because the -1/2 would be 4 minus W to the 1/2 in the denominator, to the 1/2 is a square root. Yeah, that would be totally fine. When you go to plugging in, this is an easier form than this. But when we go to take the second derivative, you're going to want to leave it here. Okay? So there is a second derivative, which is just the derivative of the first derivative. We're not there yet. A couple weeks. Okay, so let's look at this one. What does d dt tell us?
The derivative.
Take the derivative with respect to t. So this is an instruction. Take the derivative of this. So if I'm looking at this, what's one way before today that you would know how to do this? Before today? Quotient rule, right? Quotient rule, it just happens that that's a 1, so a bunch of stuff is going to drop out. So this you could totally do a quotient rule way. But you could also rewrite this way. And, an exponent in the denominator, we can always bring that up. But now what does that look like? There are a lot of parentheses in my team. Let me make my table small.
chain gang.
It looks like a chain rule, right? I have something to the negative 2. Do I know, is that a power? That's a power. I know x to the minus 2. Now I have something